Welcome to the first lecture in Math 1342, Elementary Statistics. This is Professor Michael Bailey from Dallas College. We'll be using the McGraw-Hill textbook, Essential Statistics, coupled with ALEKS, the online system. In front of each of these lectures, there is a list of objectives for each lecture. I'm not going to read through this, but you can pause and identify it or put it in your notes if you choose. Statistics is an investigative process. Specifically, it's a scientific process where we're trying to answer a question. In the months leading up to an election, polls often tell the percentage of voters that prefer each candidate. Polling follows a process that is typical in statistics. And in that process, it always starts with questions. Some question that you have. In this example, it's about who is likely to win the election. But maybe you have a question about your community and support or non-support for an initiative. Maybe you're a researcher and have questions about how levels of income impact decisions or levels of education. So all statistics, all studies, all research starts with some question that you want to answer, and that's the biggest foundation for your statistical study, because it's going to direct other parts of the process. Once you have questions, then you have to collect data needed to answer those questions. And a lot of people think this is easy. Oh, I know what my question is, so I'm just going to ask questions about what my theory or question is. And formulating those questions in a rigorous way that doesn't create bias or misinformation is not exactly as easy as people think. We take surveys, so we think we can make questions. That's like eating at a restaurant and thinking you can cook. Once we have collected the data, we describe the data, and there are specific ways, scientific methods for describing this data, again, to try to keep it as accurate as possible. And then from that, we draw conclusions, again, using appropriate scientific methods. So the first kind of vocabulary we need to talk about is statistics itself, and it's just the study of procedures for collecting, describing, and drawing conclusions from information. A big distinction here is what the difference between a population and a sample. A population is the entire collection of individuals about which we're seeking information. A sample is a subset of that population containing the individuals that are actually observed or that actively respond or participate in our statistical study. It doesn't mean a population has to be literally the entire population. For example, we may be talking about a population of students at one university or at one campus. A population just is how we define it relative to the question we're trying to answer. But a population is the entire collection of individuals, and a sample is a subset of those. Simple random sampling. When we take a sample, and in most statistical studies, you have to take a sample because it's just not practical to try to get everyone in the population to respond, and it may also be costly, so you might not have the resources to do that. So we want our sample the data we collect from our sample to represent the population as closely as possible. There are no methods that can absolutely guarantee this, but the best sampling methods, and when I say sampling methods, the best methods to find the sample, all involve random selection. The most basic, and in many cases the best, is a simple random sampling. Random being something that's not ordered. A simple random sample of size n is a sample chosen by a method in which each collection of n population items is equally likely to make up the sample. So what we're saying here is a simple random sample of size 10, n being equal to 10, is a collection of 10 individuals, whatever the population is. And when we select 10 out of the population, we're equally likely to pick any one. Okay? You might think of it like a lottery. If you have 10,000 lottery tickets are sold and 5 are drawn as the winning tickets, every collection of 5 tickets that can be formed is equally likely to be in that group of 5 winning tickets. So on this image, on this slide, you see this little paw prints. I call it paws. And so the idea here is that when you see this, it's a good idea to pause the video, read through, and see if you can answer it on your own first. These are all questions that give you a chance to kind of actively participate with the video. So go ahead and hit pause and then answer the question, on your scratch paper or whatnot, or in your head, and then hit play and continue on. A physical education professor wants to study the physical fitness levels of 20,000 students enrolled at her university. She obtains a list of all 20,000 students, numbered from 1 to 20,000, and uses a computer random number generator to generate 100 random integers between 1 and 20,000, then invites the 100 students corresponding to those numbers to participate in the study. Is this a simple random sample? Yeah, this is a simple random sample because any group of 100 is equally likely to be chosen, because she used a random generator to identify 100 students out of 20,000. The way that works is they have numbers between 1 and 20,000. The computer just spits out supposedly random. Of course, computers aren't totally random, but it's pretty close to random. Here we have another pause. So hit pause, read the question, and then try it. The professor in the last example now wants to draw a sample of 50 students to fill out a questionnaire about which sports they play. The professor's 10 a.m. class has 50 students, so she uses the first 20 minutes of class to have the students fill out the questionnaire. Is this a simple random sample? Again, if you haven't, go ahead and hit pause and then answer the question. This is not, because the students aren't selected randomly. She selects all these students in her class, as opposed to 50 out of the 20,000 students randomly. So there is no, it's not like a lottery. Only those 50 students would be winning tickets, and anyone not in her class has no chance of being selected. One more. A pollster wants to understand the proportion of voters in a certain town who are Democrats. He goes to a large shopping mall and approaches people to ask whether they are Democrats. Is this a simple random sample? Again, hit pause. No, this sample consists of people in the town who visit the mall, and possibly aren't even people from the town. There could be people from neighboring towns in the mall. So there's a number of issues with this sample beyond being not random. Another one. Hit pause. A telephone company wants to estimate the proportion of customers who are satisfied with their service. They use a computer to generate a list of random phone numbers and call those to ask them whether they are satisfied. Is this a simple random sample? Yes, every group of n customers where n is the sample size is equally likely to be chosen. Samples of convenience. In some cases, it's difficult or impossible to draw a sample in a truly random way. In these cases, the best one can do is to sample items by some convenient method. A sample of convenience is a sample that is not drawn by a well-defined random method. Let's look at an example. A construction engineer has received a shipment of 1,000 concrete blocks delivered in a large pile. The engineer wishes to investigate the crushing strength by measuring the strengths in a sample of 10 blocks. Explain why it might be difficult to draw a simple random sample of blocks. Now, this isn't about statistics, this is about common sense. So think about it, hit pause for a minute, and think why might it be difficult to do a random sample of 10 blocks? Okay, imagine you have 1,000 blocks in a pile. It's going to be very difficult to reach which blocks. The blocks on the bottom, the blocks in the center, really probably blocks, 5 or 10 deep. So this is just a physical restriction that makes random sampling very difficult. The other part, you'd have to number all the blocks. So there's a number of reasons why this wouldn't be very convenient, or wouldn't be easy to do a simple random sample. So one way to draw a sample of convenience would be to simply take 10 blocks off the top of the pile. And you might want to, pick them to be more random, to not pick, the first 10, to pick them in different spots on the top of the pile. The problem with samples of convenience is that they may differ systematically in some way from the population. If it is reasonable to believe that no important systematic difference exists, then it is acceptable to treat the sample of convenience as if it were a simple random sample. But it would be wise for any statistician who did this to also explain that they didn't use a simple random sample, and explain why they picked the convenience sample and why they trust that data. A stratified random sampling. In stratified random sampling, the population is divided up into groups, and this is the strata, groups called strata. Then a simple random sample is drawn from each stratum. Stratified sampling is useful when the strata differ from one another, and it's related to your question. For example, maybe you want to compare how males answer, what male opinions are versus female opinions. Okay, so the strata differ, the groups differ from one another in some characteristic, but the individuals within a stratum tend to be alike. And again, this is usually related specifically to the topic or the question that you have formed. A company has 800 full-time and 200 part-time employees. To draw a sample of 100 employees, this is a different example of a stratification. So the company, to draw a sample of 100 employees, a simple random sample of 80 full-time employees is selected, and a simple random sample of 20 part-time employees is selected. Now, why did they do that? Because 80% of their employees are full-time and 20% of their employees are part-time, as you can see from the numbers. So they're trying to use those percentages to give more weight to full-time employees who create a larger part of the population. It's an interesting stratification. In some ways you may not care about that. So again, it's related back to your question that you're forming, because if full-time versus part-time doesn't really apply to what you're trying to investigate, then you probably don't want to stratify this. You just want to get opinions across the board. Or you might stratify it in 50-50%, not related to the percentage of employees. So there's a lot of thought that goes into this. And we're not talking brain surgery. We're really talking a lot more common sense. And it's really easy to overlook some of these things as well. Cluster sampling is when items are drawn from the population in groups or clusters at random. Cluster sampling is useful when the population is too large and spread out for a simple random sampling to be feasible. To estimate, I think it's easiest to look at an example here. To estimate the unemployment rate, a government agency draws a simple random sample of households in a county. Then someone visits each household and asks how many adults live in the household and how many of them are unemployed. So in this example, the clusters are the groups of adults in each of the households in the county. This is a cluster sample because a simple random sample of clusters is selected. The clusters is basically a household, okay? The group of adults in the household specifically, but it's basically a household. And so then they pick so many households to look at. Every individual in each selected house, in each selected cluster, is part of the sample. Systematic sampling. In systematic sampling, items are ordered and every kth item, and k being a number, so you might say every seventh item is chosen to be included in the sample. Systematic sampling is sometimes used, it's often used to sample products as they come off an assembly line. We take every 99th item off the line, or maybe every 1,000, depending upon what the production order is. In order to check that they meet quality standards. This is a very typical way in manufacturing. Automobiles are coming off of an assembly line. A systematic sample will be drawn for a detailed check. The starting point will be the third car. Then every fifth car after that will be sampled. Which cars will be sampled? Again, this is not rocket science. It's very common sense. We start with the third car. Then we pick the fifth car after that. So 3 plus 5 would be 8. And then the fifth car after that, 8 plus 5 would be 13. And so you can see the results of that sample there. Don't overthink this stuff. Most of it's common sense again. It's not rocket science. These figures, I'm going to just go ahead and pull all of them out, are a visual representation of the different sampling techniques. These may help you. I was going to say that when I looked at these, it took me a while to kind of relate each of the sampling techniques to the diagram. But then I guess, in a way that kind of helps you strengthen your definition and your understanding of each of them. For example, the first one, we're just picking random numbers as we go through here, right? So there's no pattern you can hopefully can detect of the number or when people are selected, especially if you just went across the rows. In the simple stratified, you can see each strata is alike, and then they're taking 2 from each one. So, if you kind of look at these and figure out how did they make this visual representation of the definition, that may actually help your memory and your recall of the different methods. Voluntary response samples are often used by the media. You see these all the times on TV if you watch the evening news. There's always polls where you'll see at the bottom of the screen, call this number, use our app, and tell us what you think. So voluntary response samples we see a lot of places. Even in reviews of items like on Amazon or Yelp, etc., these are voluntary response samples. The review is being done on a voluntary basis. And again, here we have a radio announcer. We'll invite people to call. Voluntary response samples are never reliable for the following reasons. People who volunteer an opinion tend to have a stronger opinion than is typical of the population. People with negative opinions are more often likely to volunteer their response. And this is just scientifically studied, statistically studied, that people with negative opinions are much more likely to take the time and energy to respond to a survey or a review. Now, I will say that in a scientific study, in a statistical question that I have that is important, I'm not going to use a voluntary response. But do I rely on them? I rely on them heavily. When I Google for restaurants, when I look for something to buy on Amazon, and I use some techniques that are actually not totally consistent, but it's not as big of a in importance. I'm not evaluating the efficacy of a medicine, etc. I'm trying to find the best product. If I see a product that only has 3 reviews and it's a 4, versus a product that has 10,000 reviews and it's also at a 4, that gives me greater confidence in my purchase. And so it's less risk on my part, it's less importance. So I'm going to just let you page through these. I'm not going to talk through them. These are all pauses. So read the first one and the second one and see what you think. These are just a chance to kind of review the material on your own. Continuing on with 2 more examples, you can hit pause and answer both of A real important vocabulary is the difference between a statistic and a parameter. This is just vocabulary. Statistic is a number that describes a sample or relates to a sample, and a parameter is a number that describes a population. They technically could be the same number, but they're based upon whether you actually got that number from a sample or you actually got that number from the entire population. For example, we might say 30% of Dallas College students prefer algebra over statistics. If we did a sample, that number, that 30%, is a statistic. If we literally or actually polled the entire population, that would be a parameter. And so that's the only difference. These are easy to remember. Notice statistic and sample both begin with S. Parameter and population both begin with P. Here you go. You can test yourself again with a little pause here, determining which of these is a statistic and which of these is a parameter. 57% of the teachers at Central High School are female. This is talking about all the teachers at the high school, so it's talking about a population, not the population of all teachers in a city or county, and then this sample there. So this is a parameter. In a sample of 100 surgery patients who were given a new pain reliever, 78% of them, this tells you that we're talking about a sample, so this is a statistic. So also following up each of these presentations, I'm leaving in these kind of outlines of the things that you should know from this section of the book. You can go back to the book, you can go back to this presentation or the PowerPoint, whatever works for you. Again, I'm not going to review these. You can read through these hitting pause to keep the videos as short as possible.